Okay, here in this video, we're going to talk about waves that change in both space and time. Imagine waves out on the ocean. Like if you look out on the ocean and you take a photo of the ocean, you can see a wave. It'll look like a sine wave or a cosine wave. But if you watch a bird sitting in the ocean, so you just watch one particular location, you'll see that bird bounce up and down. So that's just a wave in time at one particular location. So in the real world, sound waves, waves in the ocean, waves in space travel in both space and time. So we know from trig, what we learned is we might have, say, some cosine function. Y equals A cosine bx plus c plus k. And we were told that that wave has a period of 2 pi over b. That's what you've learned and memorized. Well, we're going to expand on that. We're going to have some function that looks like this. Y, the height of the wave depends on both your position and your time. It's a function of 2 variables. And it could be a sine or a cosine. But we'll have some A, some cosine of, say, k times x, completely different from this k, not even related. And then plus or minus, we might have a plus there or a minus, some omega times t. Okay, as you may have guessed, the number in front, a, in absolute value, the absolute value of a represents the amplitude of the wave. That's how high and low it goes above the midline. But now I've got 2 variables in here, so I'm going to have 2 versions of what we've called period. There's going to be regular old period, how long it takes in time between 2 different crests. And that's going to be related to the number in front of t, which is time. So this is omega, our period, capital T, is 2 pi over omega. That's how the time it takes if you're watching a bird on the ocean, watching the bird go all the way down, back up, and back to its starting point. Time in seconds. Another concept we're interested in that's related to period is frequency, and that's just 1 over the period. So if this is in seconds per cycle, frequency is cycles per second. How quickly is that bird going up and down? How many times does it go up and down per second? We call that the frequency. That's measured in hertz. Okay, now that's just one version of what we've always called period. There's another one in space. And we call that the wavelength. That's the distance in meters between different crests. And that will be 2 pi over the number in front of x. X is in meters. 2 pi divided by k will give us our wavelength in meters. This number omega here, right there, is called the angular frequency. That's in radians per second. And then we can combine some of these together to get what's called the wave speed. This is how quickly a wave is moving through space and time. And the formula for that is just V equals lambda times F, or lambda divided by T, meters per second. Lambda is the distance in meters. T is the distance, quote, in time, meters per second. Okay, let's look at an animation and this will become a lot clearer. So I'm going to turn on my faucet here and that's going to make waves. Notice that this wave is changing in both space and time. So if I were to pause it, so I've frozen time, I'm only looking at space, I've got some kind of sine wave. The wavelength is the distance from one crest to the next. I can get my little tape measure out here and I can measure that. So for this particular one I've drawn, the wavelength is about 2.5, 2.6 centimeters. That's the distance from one crest to the next. Or I could just watch this one little location right here. So maybe I just watch this spot right here. Watch that spot go up, down, up, down, up, down. Sometimes it's easier to watch here on the side. Look right here at the edge. I'm going up, down, up, down. If I were to put a bird in the water here, the bird would be going up and down. The time it takes to go through a complete cycle is called the period. And I got a little measurement here. I could just time how long it takes between drops here. So start. So about 1.68 seconds roughly is my period. That's how long it takes for a wave to go all the way up and down. And I could graph these out. I could graph out so here I'm graphing out the height at this particular position as a function of time. So up, down, up, down. So we can see that graph. The time between one crest and the next is called the period. If I turn down my amplitude here, I'll be able to see that a little better. So that time between one crest and the next crest is what we call the period. The distance between one crest and the next crest so now I'm measuring what we're seeing. I'm measuring a snapshot. I'm taking a picture of the ocean. So time is frozen right now. And I'm just looking out at the ocean, and the distance from one crest to the next we call the wavelength. So we have two different versions of what we used to call period. The one that's in space is called wavelength. The one that's in time is what we call period. Okay, so got a couple examples written out here. So I've got some kind of sine wave here, and I've frozen time. I took a picture of time. I want to figure out from here what is my wavelength. What's the distance from one crest to the next? So this is one complete cycle to here. To right here. One complete cycle all the way up and down. So we go all the way up, down, all the way back to the beginning. There, see, there's one cycle of sine. What's that distance there? 6 meters. That's what we call the wavelength. 6 meters. Now, I'm just watching one particular location, x equals 0. So I'm zooming in on one spot. I'm watching that one spot go up and down. I've got a bird in the ocean, and it's going up and down and up and down. So I'm measuring time versus height. So how long does it take that bird to go through a complete cycle? 4 seconds. That's what we call the period. Wave speed How fast is energy traveling along this wave? Wave speed is lambda divided by t. Distance divided by time. Meters per second. So 6 divided by 4 would be 1.5 meters per second. That's how fast energy is traveling along the wave. And then frequency is just 1 over the period. 1 divided by 4 is 0.25 hertz. Okay, here's another example. So now somebody has handed me a wave in function form here, and I've got to figure everything out. So A gives us the amplitude. Absolute value of A is the amplitude, and that's measured in meters. So this wave will go up and down 3 meters above and below the midline. The number beside X we call K, and that's related to the wavelength. The wavelength is 2 pi divided by K. So that's the distance from one crest to the next, half a meter. 2 pi divided by 4 pi would be 0.5. Omega is that number beside t. That's related to the period. How fast this thing's moving, or how long it takes to go through a complete cycle in time. And the period is always 2 pi over omega. 2 pi over 6 pi. We just ignore the negative here. The pi's cancel, and we get 1/3, about 0.33 seconds. And then the frequency is just 1 over the period, 1 over 1/3, just flip that over, we would get 3 hertz. So we can look at graphs of this. So I'm going to take this formula here, and I'm going to plug in x equals 0. So literally, I just plugged in x equals 0. That's all 0. We'll get this graph here, where we're looking at time versus position. And we can see here that this thing goes through 3 complete cycles in 1 second. See, I start all the way up. There's 1 cycle, 2, 3. That's my frequency, 3 cycles per second. Or the period would be this time here, from here to here, 1/3 of a second. That's our period. Or I could take that same formula, plug in t equals 0. My time now is 0. I'm just watching one particular location. And I would get a graph that looks like this. And we could see here that the distance from one crest to the next is half a meter. That's my wavelength. And that's a good place to stop.